Quicksort is one of the fastest sorting algorithms out there, but it can also be one of the hardest to understand. In this video, we'll go through exactly how the Quicksort algorithm works in detail in a way that I promise you'll understand. Then we'll walk through coding our own Quicksort implementation in Java. My name's John, I'm a lead Java software engineer, and I love sharing what I've learned with you in a clear and understandable way. I also have a full Java course available and a link down in the description if you're interested. Let's get right into it. Okay, before we just dive into Eclipse and start coding, it's important to know how the Quicksort algorithm works. The whole Quicksort algorithm is basically just 3 steps. The first step is choose one of the numbers in your array as the pivot. So you might be thinking, what do you mean choose a pivot? I just choose any number in my array here as my pivot? And essentially the answer is yes. It's not so much that the pivot you pick isn't important, but how you choose a pivot isn't important to understanding the actual algorithm. What we're going to be doing is just choosing the last element in the array as the pivot, and I'll show you how that works. Then at the end of the video, we'll go over a better strategy for picking the pivot, which is also still really easy to implement. After you've chosen the pivot, the second step is to move all numbers in the array that are lower than the pivot to the left of it, and all numbers that are higher than the pivot to the right of it. This step is also called partitioning. So since we're using the last number as our pivot, in this case it will be 7. And the partitioning step will put all numbers less than 7 on the left side of the 7. So that means that the 1, the 3, the 4, and 5 will all be moved to the left of 7. And 8 and 9 will be moved to the right of 7. So after that partitioning step, all the numbers to the left of 7 are smaller than 7, and all the numbers to the right of 7 are larger. And the number that we chose for our pivot, the 7 in this case, is actually in its final spot in the array. The partitioning step is probably the most complicated to code, but don't worry, we'll go through that part step by step. After partitioning, the third step is to recursively quicksort all the values to the left of that pivot and all the values to the right of the pivot. And when we do the quicksort for those subarrays, it's done exactly the same way we just did it. So first we would do the quicksort for the left portion here. And we'll repeat the same steps that we did before, which are first, choose a pivot. And again, we're just going to use the last number as the pivot, which in this case would be 1. Then we do the partitioning where we take any number that is greater than 1 and put it to the right of 1, and any number that is less than 1 and put it to the left. In this case, they all happen to be greater than 1, so they all go to the right of 1. Then after the partitioning step of that quicksort, we then recursively quicksort all the elements to the left of the pivot and all the elements to the right of the pivot. There's no elements to the left of the pivot because our pivot was 1 in this case, so we just have to recursively quicksort all the numbers to the right of the pivot. And again, we do that exactly the same way, where we first choose a pivot, which is going to be the last number for us, or 5. Then we move all the numbers in this subarray that are less than 5 to the left of 5, and all the numbers that are more than 5 to the right. In this case, 3 and 4 are both less than 5, and they're already to the left of 5, so there's nothing we have to swap. Then again, we recursively quicksort the subarrays to the left and right of that pivot. Since there's nothing to the right of 5, we only have to recursively quicksort the subarray to the left of 5, which is 3 and 4. Again, to quicksort this subarray, we first choose a pivot, which for us is going to be the last number in this array, 4. Then we do the partitioning again, where in this case, 3 is less than 4 and it's already to the left of 4. And then we recursively quicksort each subarray to the left and right of 4. In this case, we only have a subarray to the left of 4 here, which is just the number 3. The number 3 is just one element, so it's already sorted. So now we've completed quicksorting all of the numbers that were originally next to this 7. But remember, we still have to recursively sort all the numbers to the right of the 7. And of course, we just quicksort this in exactly the same way. First, we choose a pivot, which in our case, we're just going to choose the last number, which is 9. Then we do the partitioning, where in this case, there's no changes that we have to make because 8 is less than 9 and it's already to the left of 9. Then we recursively quicksort the subarrays to the left and right of our pivot. In this case, we only have a subarray to the left of the pivot, which is just the number 8. Since it's only one element, it's already in order and there's nothing that we have to do. At that point, we've completed all of the recursive quicksorts and we finally end with our perfectly sorted array. And now for the fun part, let's get to coding. As always with these sorting algorithm tutorials, I'm starting here with a little bit of setup just so we can test the sorting algorithm that we write. This first part will generate an array of 10 integers randomly between 0 and 99. So that just gives us a random array of ints to sort. Then we print out that array here in its initial completely random order. Then we call our quicksort method here, which we are going to write, where all the magic happens and it sorts our array from smallest to largest. And then after that, we print out the array again, hopefully in perfectly sorted order. So let's go ahead and jump into that quicksort method, which is currently completely empty, and we'll start our implementation. You may have noticed that it's actually taking in 3 parameters. The first one is the actual array that it's going to sort. That makes sense. But then it also takes in a low index and a high index. If you remember from the demo, Quicksort is a recursive algorithm where after we do the partitioning, where we put all the numbers less than the pivot to the left and all the numbers higher than the pivot to the right, we recursively quicksort all the numbers in the left partition and recursively quicksort all the numbers in the right partition. That recursive step is why we need the low index and the high index. When we tell it to recursively sort the subarray, we don't want to just tell it to recursively sort the entire array again. So we pass in basically a range, a low index and a high index of that particular subarray so that it can properly do the recursive quicksorts. However, that does make it so that when you initially call the quicksort method, in addition to passing in the array, you need to pass in the low index and the high index too, which of course when you want to just sort the entire array, the low index is going to be 0, and the high index is just going to be the last element in the array, which is just going to be the length of the array minus 1. Near the end of the video, I'm going to show you a trick where you can get rid of this for your initial quicksort call and just have to pass in the array that you want to sort. All right, now let's get to writing our quicksort method. Now, what was the first step in our quicksort algorithm? It's to choose a pivot. And remember, for our purposes, we're just going to choose the last number as the pivot. So to do that, we'll just create an int and we'll call it pivot and set it equal to the value of the array at that high index that's passed in here. Remember that this is a recursive algorithm, so we can't always just pick the last element of the entire array that we're sorting as the pivot. In any given recursive step in the middle, we might just be sorting one small subarray portion of the entire array. And that'll be passed into this method recursively with a low index and a high index, indicating that range that we want to be recursively sorting right now. So the last element of that particular range that we want to be sorting is going to be passed in as high index. Now we've done the easy part, we've chosen a pivot. Now for the hard part, the partitioning, where we have to move all the numbers lower than the pivot to the left of the pivot and all the numbers higher than the pivot to the right of the pivot. How exactly are we going to do that in the code? Here's what we're going to do. So we chose a pivot, right? That is just going to be the last number, in this case, 7. So 7 is our pivot. And for now, we're just going to ignore that and let it be and just focus on all of the other numbers. Then what we're going to do is create 2 variables that we're going to use as pointers. One we'll call the left pointer, and we're going to start at the leftmost part of the array. And the other we'll call right pointer, and we're going to start it at the rightmost portion of the array. We're going to start with the left pointer. What we're going to do is start walking through our array a single element at a time until we find an element that is larger than the pivot. So first we look at the number 1. Is 1 larger than 7? No. So then we move that left pointer over to look at the number 8. Is 8 larger than 7? Yes. So we'll stop there and leave that left pointer pointing at the number 8. And then we move on to our right pointer. And what we're going to do with the right pointer is start walking from the right side of the list, one element at a time, to the left until we run into a number that is less than our pivot. So our right pointer starts looking at the number 5. Is the number 5 less than 7? Yes. So we stop there with the right pointer pointing at the number 5. So at this point, our left pointer is pointing to a number that is greater than our pivot, and our right pointer is pointing to a number that is less than our pivot. At that point, we're going to swap the numbers at those 2 pointers. So our 8 will move over here where the 5 was, and the 5 will move down here where our 8 was. Then we repeat that process. We move our left pointer over one spot. So our left pointer is pointing at the number 3. Is 3 greater than 7? No, it's not. So we move our left pointer over to point at the number 9. Is 9 greater than 7? Yes. So we stop there with the left pointer pointing at 9. Then we move over to our right pointer. and move it to the left to look at the number 4. Is 4 less than 7? Yes. So we stop there. At this point, our left pointer is pointing to a number that is greater than 7, and our right pointer is pointing to a number that is less than 7. At that point, we swap the two numbers that our left pointer and right pointer are pointing to. Then we continue that same process. We move the left pointer over one spot. At this point, our left pointer and right pointer are pointing to exactly the same element. Once that happens, we want to stop that process of moving the left pointer and right pointer toward each other. And then what we're going to do is swap our pivot with the number that our left pointer is pointing to. So in this case, the number 9. So that will move our 9 out to here where our pivot was, and our 7 in here where our 9 was. At that point, the partitioning step is complete. So you'll notice that all the numbers less than 7 are to the left of 7, and all the numbers that are greater than 7 are to the right of 7. After that partitioning happens, we're going to recursively quicksort the subarray to the left of our pivot and recursively quicksort the subarray to the right of our pivot. That partitioning step is probably the most important part of the quicksort algorithm. Let's put what we just talked about into some code. First, we'll declare our two pointers, left pointer and right pointer. So we're going to have int left pointer, and we're going to start the left pointer at the left side of the array that we're sorting. So we can just initialize it to low index. And we'll also create an int right pointer, and we'll start it at the high index of the array that we want to sort. Now we need to create a loop that will move the left index and the right index toward each other until they hit each other. So to do that, we're going to create a while loop. And the condition of our while loop is going to be while the left pointer is still less than the right pointer. So once our left pointer runs into our right pointer, this expression will evaluate to false and knock us out of our loop. So inside of that loop, we want to walk our left pointer from left to right until we find a number that is higher than the pivot, or we hit our right pointer. So to do that, we're going to want an inner while loop. So while the value of the array at that left pointer is less than or equal to the pivot, and our left pointer is less than our right pointer. So while that is still the case, we want to increment our left pointer. So left pointer plus plus. So this will keep incrementing our left pointer until the value of the array at that left pointer is greater than the pivot. Or if it's walking from the left and never finds a value that's greater than the pivot, eventually the left pointer will pass the right pointer and will also kick us out of this loop. And we'll do exactly the same thing for walking from the right side. We'll have another inner while loop. We're going to walk from the right until we hit a number that is less than the pivot, or until we pass our left pointer. So it's going to look very similar. While array at right pointer is greater than or equal to the pivot, and left pointer less than right pointer. Because we want to move the right pointer from right to left, we actually have to decrement it each time in the while loop instead. So we'll do right pointer minus minus. At this point, we have a left pointer that's pointing to something that is larger than the pivot, and a right pointer that is pointing to something smaller than the pivot. And now we just want to swap those two numbers. Since we're going to have to do that swapping in a couple of places in our algorithm, it's probably the best to do that in its own private method. So let's scroll down here and create a new private static void method that we're going to call swap. And it needs to take in 3 parameters. One is the array that contains the 2 elements that we want to swap. Then it also needs to take in the 2 indexes that we want to swap. So int index 1 and int index 2. In order to do a swap, we just need to create a temporary variable. We'll just call it temp to hold one of the values that we want to swap. So int temp equals array of index 1. Then we set the value of the array at index 1 equal to the value of the array at index 2. Finally, we set the value of the array at index 2 equal to our temp variable. So back up here in our quicksort method, remember that at this point we wanted to swap the elements that were at our left pointer and right pointer. So to do that, now we can just call our swap method and pass in the array and also the left pointer and right pointer as the indexes that we want it to swap. So what these while loops will do is keep moving the left pointer and right pointer closer and closer to each other, swapping elements when it needs to, until those pointers meet. Now remember from our demo that at that point, what we want to do once our left pointer and right pointer meet, we want to swap our pivot in with the value that our left pointer is pointing at, like this. So to do that, it's very easy. We can just call our swap method again, pass in the array, and we want to pass in our left pointer as the index of one of the elements we want to swap. And for the other index, we actually want to pass in high index. And that's because we know that this high index will be the index of our pivot, because we've always chosen the last element as our pivot. At that point, the partitioning step is done. All the numbers that are lower than the pivot should be to the left of it, and all the numbers higher than the pivot should be to the right of it. So the only step left is the recursive step, where we're recursively quicksorting the partition to the left of the pivot and recursively quicksorting the partition to the right of the pivot. So first, let's make the recursive call for the partition to the left of the pivot. So we'll recursively call our quicksort method. We need to pass in our array, but we also need to pass in a low index and a high index. So at this point, remember, our pivot is right here. So what we want to do is call quicksort for just these 4 elements. So what do we need to use as the low index and the high index that we pass in? Well, our low index will just be the very first number in the array that we were sorting in the first place, right? And that was passed in as low index to this method. So for the low index, we can just pass in low index. Now for our high index, we want it to be the last element in this subarray that we're sorting. Now since our left pointer is going to be pointing at our pivot here, the high index of this left partition is actually just going to be our left pointer -1. So we can just pass in left pointer -1. Next, we need to recursively quicksort the right partition. And to do that is going to be very similar. We'll call the quicksort method recursively, pass in our array. So what do we need to pass in for our low index? Well, it's just going to be one number past our pivot, which is where this left pointer is pointing. So we can just use left pointer +1. So we'll just pass in left pointer +1. And for the high index that we pass in, we can just pass in the high index of this entire array that we were sorting. So we can just pass in high index. Before we finish this algorithm though, there's still one case we haven't accounted for yet. And that's the case where as these recursive calls keep going and going, eventually it's going to be told to recursively sort a list of just one element. At that point, because an array of just one element is already sorted, it can just return. There's nothing that it has to do. So we actually want to put that logic here at the top of our quicksort method. So here, if the low index is greater than or equal to the high index, then we know we're dealing with a subarray of just one element, and we can just return, and there's nothing else we have to do. Okay, and with that, that should give us a working quicksort. So let's go ahead and run our test program with 10 random ints and see if it works. Here we go. Okay, so it printed our before in completely random order, and then printed the after, where everything looks to be perfectly sorted. Awesome. Let's go ahead and run it a few more times just to make sure everything is looking okay. Okay, so now that we know our quicksort algorithm is working, let's do a little bit of code cleanup to kind of optimize it, and then we'll see exactly how fast quicksort is. First, just for code readability, remember how we had 3 main steps in our quicksort algorithm. Choose a pivot, do the partitioning, and then do the recursive quicksort calls. So here in this whole section, right after we choose the pivot, but before we do those recursive quicksort calls, this is basically all partitioning code. So it might be nice to split this out into its own method. So to do that, you can just highlight all the code that you want to put into that partition method. And if you're using Eclipse, you can hit Alt-Shift-M. That'll pop up this window here, and all you need to do is name the method that you want to create. So since this will be our partition method, we will call it partition. Then just go ahead and hit OK, and it automatically created our partition method with all the code that we wrote. So now our quicksort method is even easier to read. Choosing a pivot, performing the partitioning, and then recursively quicksorting the left and right partitions. Next, I mentioned at the beginning of the video that how you choose the pivot can be important because there are certain situations where if you choose the pivot really poorly, it could result in worse average performance for Quicksort. So while choosing the last number in our array does work fine, a strategy which ends up with a bit better average runtime is actually choosing a pivot at random. That might sound like it'll be really complicated to implement, but it's really just a pretty simple modification to what we have so far. Here's how that's going to work. So we're going to choose a random element in this array as the pivot. So let's say we randomly choose the number 3. Instead of trying to do the partitioning with this 3 still in this same spot in the list, what we're going to do is actually swap this element with the last element in our list right away. So that way the 3 that we chose as our pivot is now at the end of the list and completely out of the way. And at that point, after we've swapped that pivot and put it at the end of our list, everything else works exactly the same way that it did before. We do the whole partitioning step with the rest of the array, and at the end of that step, we still swap out our pivot with the index of our left pointer. So to do that in the code, we're going to start here by creating an int that we'll call the pivot index. This is going to be the index in our array that we're going to choose randomly as our pivot. And in order to choose that randomly, we are going to use the random class. So we'll say new random.nextInt. And what we're going to pass into this method is high index minus low index. And then we're actually going to add the low index. This calculation will give you a random index somewhere between the low index and the high index that are passed in. So now instead of just using the value of the array at the high index, we want to choose the value of the array at the pivot index that we just randomly generated. And then we need to do the swap that we talked about, where we swap that random pivot with that last element of our array. So to do that, we can just do swap, pass in our array, and then swap our pivot index with the high index. So that's all you need to change in order to choose your pivot randomly. So you should be able to rerun your code. Everything should still be sorted perfectly, except your algorithm will now perform a little bit better in the average case. One other thing here is that it's kind of ugly that at the beginning, when you call this quicksort method initially, you have to pass in the low index and the high index. It would be nice if you could just pass in the array that you want to quicksort like this. Well, what we can do is actually create another private method, and we'll actually also call it Quicksort. So we will overload the Quicksort method. Overloading is when you have more than one method that has the same name but different parameters. So in this case, we'll only take in the array that we want to sort. So this isn't the method that we're going to be calling recursively. We'll only call it the first time when we want to initiate the Quicksort. All we have to do in this method is call this other Quicksort method that does take in the low index and the high index. So we'll just call that other Quicksort method, pass in the array, and just as we did before, we'll pass in 0 as the low index and array.length minus 1 as the high index. So now we should again be able to rerun our program and have everything work exactly as it did before. The only difference is now you can kind of call this quicksort method a bit more naturally, where you just have to pass in the array that you want to sort. Now that we have everything fully optimized, let's crank this up and see how fast quicksort actually is. So instead of just sorting 10 numbers, we're going to have it sort 1,000,000 numbers. And instead of doing between 0 and about 100, we'll do between 0 and about 10,000. Okay, it took a while for it to print out, but it's already printing out the completed lists. All right, that finished really quickly. I think most of the time it took there was actually just printing out the initial 1,000,000 numbers. So what I'm actually going to do now that we know that the algorithm is working, I'm going to take out the steps where it's printing the array out, because I think that's probably taking the most time. All right, let's go ahead and run that again. 1,000,000 numbers. Okay, it was done basically instantly in less than 1 second. So let's crank this up to 10 million. Okay, that did take a little bit longer, about 5 seconds. Let's keep going and do 100 million. Okay, so at 100 million, we actually hit a stack overflow error. So what's happening here is that just due to the sheer size of the array that we're sorting, it ends up having to make tons and tons of recursive calls. And each time it makes a recursive call, it adds that method that it's calling onto something called the stack. And there's only a certain amount of memory allocated to that stack in Java. And once you hit that limit, you get a Stack Overflow error and there's just nothing you can do about it. But still, for sorting an array of 10 million elements in less than 5 seconds, that is pretty awesome. And that's why Quicksort is generally regarded as the fastest sorting algorithm out there. If you enjoyed this video or learned something, please let me know by hitting the like button, and be sure to subscribe so you don't miss each new Java tutorial. And after you make sure you completely understand Quicksort, don't stop there and keep your momentum going by watching one of these other Java tutorials below. Thank you so much for watching. I really appreciate you being here with me. I'll see you next time.